Knowledge distillation, which is alternatively called as student-teacher or teacher-student approaches as well, is about distilling the knowledge from one teacher model to train another model, which is referred as student model. So usually it is mainly used for model compression, like distilling knowledge from a bigger model to a smaller one. But it is also used for to train, for example, a generalized model of different teachers, or just to improve ASR performance without model compression as well. But the one thing, like the previous work that has been done with these approaches, have been done for the models where the output classes of the teacher model and the student model are exactly same. Or even if they are not exactly same, the teacher model should contain all the classes of the student model. So then in the work with this approach in multilingual speech recognition is where we have a multilingual model which has the classes of all the languages it contains, and then the model then the knowledge can be transferred to a language the of which the tokens are already in this teacher multilingual model. But if we want to distill the knowledge from one language to the other one, and if they have different tokens, then it is not possible to distill the knowledge given its limitation of having same output tokens for teacher and student models. So the previous work in multilingual knowledge distillation has not been done or explored this kind of thing, like how to do that. And if you see that there are a lot of languages out there in the world which are acoustically similar but written in different scripts. For example, Urdu and Hindi, and Turkish and Kazakh, and Greek and Armenian. These pairs are quite similar in spoken, but it is like in writing scripts they are different. But so I mean, when they are acoustically similar, it could be beneficial to distill knowledge from one of them to the other one because they are very acoustically similar, but because they are written in different script, so they have different. Their ASR model will have very diverse output token, so we can't distill knowledge from in these scenarios. So our motivation of this work was like, is there any way if we can distill knowledge from a teacher model to a student model which have very diverse output tokens? So to that end, we propose a novel approach to overcome this limitation using our previously proposed cross-lingual mapping approach. And then the other thing that we did in our previous paper that I didn't cite here, I cited that somewhere later, but we observed that the ensemble of different teachers really help in improving the performance rather than single teacher. So here we propose a self-adaptivating scheme where we, rather than having in the ensembling technique, having just only selecting one teacher at a time, we are weighting the teachers, and the teacher weights are self-adaptive, which means we adopt a different weight for each teacher for each utterance depending on the confidence of the teacher. But before going into that, I will be just recapping what mapping models that we previously proposed. So actually what we do in mapping model, or what is a mapping model, is like for each language, for a target language, a mapping model is basically just a model which transforms the posterior distribution from one acoustic model to the other. So it is basically, for example, if we have a for a target language, we get an inference of this language utterance from source language ASR models. Source language, by source language, like we mean any other language. So for example, if I have a target language X and I have source language acoustic models, this S1, S2, and Sn. So I'm basically the input of this mapping model is the posteriors from the acoustic models of the source languages. This PS1 is the posteriors from the ASR model of S1, given the target speech utterance. PS2 is the posteriors from the S2 source language acoustic model given the target utterance and so on. And then what mapping model does is like, because when we are giving the input utterance to S1 ASR model, it will have the posterior distribution of S1 model, but the mapping model will transform it to the posterior distribution, which looks like actually the target language ASR model. So how did we train it? I'm not gonna discuss that in detail here. If you're interested, you can go to our previous paper, but it is usually trained on very limited data. For example, all the models here, I will be discussing it soon, but all the models here are trained on very limited 29 hours of data, and that is still pretty good. And here I will go to machine learning, that how we are doing overcoming that limitation of knowledge distillation when we have different output tokens for student and teacher. So here is so the teacher model in our scenario in machine learning is not then the acoustic model, just an acoustic model of some other language. If I want to use acoustic model of some other language as a teacher model, then we have a mapping model as well on top of that. So actually the teacher model for one target language is then the source language ASR followed by the source to target mapping model, which is a teacher model. And here in our experimentation, we are using, we did experimentation with multiple teacher models as well. So with single teacher and with multiple teachers as well. So in multiple teachers, we have multiple teachers, and then we do ensemble weighting strategy, and which is, I will talk about self-adaptive weighting, and there are various weighting strategy that we are using a lot of from the literature as well. So then we have this the ensemble weighting strategy, and then the student model is trained with this loss. So basically, the ASR models are like whether the teacher model or student model. The ASR model are encoder, decoder, sequence to sequence models, which are basically trained with the loss of like weighted loss of CTC and sequence loss. So this loss here is basically the loss for teacher training, which is some weighted sum of CTC and sequence losses. And then in the student level training, this sequence loss is basically the CTC loss will remain the same as here in this equation, but the sequence loss is then replaced by the weighted sum of knowledge distillation loss and the previous sequence loss, actually the sequence loss. And the knowledge distillation loss here is basically the weighted sum of losses from all the teacher models, and which is the loss of teacher model is basically just the KL divergence loss between the student posteriors and the teacher posteriors. So now, because the posteriors are from, if the posterior are just from the acoustic model of the source language, we can't take this, the posterior will be quite diverse, and we can't take this loss from theirs. But here, these teacher posteriors are basically the output posteriors from the mapping model, after the mapping model. So these are basically the teacher posteriors, and we calculate the teacher loss here. And then we have this student loss here, which is the combination of soft labels and hard labels, and the student is trained in that way then. And as I said, we have tried different ensemble weighting strategy, but we propose one here, which is self-adaptive weighting. Yeah, like rather usually what kind of weighting strategies are there? Like one very conventional one is teacher averaging, where we just assign the same weight to all the teachers. Or then there is frame-wise maximum, where we select the for each frame where we have the which teacher has the maximum value, we just select that posterior. But rather than doing these kind of things, we are defining a self-adaptive weighting, which assigns the weight to each teacher loss, but these weights are based on the like the so-called performance or the confidence of the teacher model. So what we do actually is we take the for one given utterance, we take the maximum value for all from the posterior for all the frames, and we take the average of each, and then the weights are basically are basically calculated in this using this equation, which is basically assign the weights based on this mean maximum value. But using this tau parameter, we are actually basically uh, diverging, like assigning a weights which are statistically significant. Like otherwise, the weights will be very close to each other, but we are just trying to disperse them a bit based on their performance. So having the different values of tau will give you different will disperse the weights more if you select the greater tau value. So now about the experimentation, the data sets we have used, it's from our previous experiments. So we are using 4 low-resource languages from our probable speech corpus, which are Tamil, Telugu, Saban, and Javanese. So for ASR training, we are using the full language pack train set for training, and for the evaluation, the depth set of Babel corpus. And for the mapping model training, again, for training, we have randomly sampled 29 hours. And for depth set, we randomly sampled disjoint 1 hour set, and the val set is same as the AS or trainee. But one more important thing to note here is that all utterances without any speech or longer than 20 seconds speech are discarded here because of some computational limitations. So these are the mapping model accuracies, which are mainly from our previous work of InterSwiss 2023, but these are just to show how the mapping models are performing, which we are using here. So for example, for the target language of Tamil, the accuracy from Telugu source language is 47.46, and by the accuracy we actually mean like the ratio of correctly mapped frames to the total number of frames. And one correctly mapped frame is if the argmax of the mapped posterior is same as the argmax of target posterior. So you can see that for Tamil, it is in the range of 45 to 47%. And in Javanese, it's little better. For Telugu, it's 54, but for Tamil and Sabana, it's 62 to 65. So then we are using these mapping models here and for each teacher. And but before going into the student model performance, I will explain so we basically calculated the performance of teacher model actually, the ensemble teacher models by applying greedy decoding on top of that. And we tried for different ensembling techniques, which are LET sampling that we proposed in our last paper in ICAPS 2023, which was about the generalization of different domains for English language. So we tried LET sampling, we tried frame-wise maximum, and the teacher averaging, and I proposed self-adaptive weighting. So I will just go to the average of all the languages. So you can see that the LET sampling didn't work here for us. For in multilingual case, not very well. And the frame-wise max was a bit better than that, but student self-adaptive weighting that we proposed here and the teacher averaging, they were kind of same. So now using these techniques, we have to train a student model for each of these languages, but we are just using the top 3 ensembling techniques. Like we'll do just the experiment for frame-wise max, self-adaptive weighting, and teacher averaging, and the single teacher model as well. So here are the most students, the performance of the student model after training with the data loss of hard label and soft labels. So you can see that the first row is monolingual ASL baseline, where we have trained the same model, same capacity, same architecture, but only using the language dependent data. And you can see that the average character error rate here is 43.2%. And using the teacher averaging, it was worse than the monolingual, and it goes to 44.2%. But with the self-adaptive weighting, it's 42.9%. And then it's with the single teacher. So in the single teacher, we actually just selected the one teacher, and that teacher is basically the language which is uh, closer to the target language. And then the point is, how did we select the closer, or how do you define the closer language? So the closer language is where we have the maximum mapping model accuracy for the target language. And intuition to do that is basically because the performance of the student model is based on the performance of teacher model. And our teacher model is a combination of ASR model and the mapping model. And so it's the performance of student model fairly depends on the performance of mapping model actually. And you can see that for example, for the Tamil, the performance is uh, for the mapping model is in the range of 45 to 47, and you can see in the result for the Tamil language, like it's 44.3% for monolingual baseline, and it just improved to 43.8% in for even with the single teacher. But because the performance of mapping model is fairly good for the Javanese, so in the Javanese you can see that it's 41.9 to 37%, which is about 4% improvement. So the performance is basically fairly depends on the performance of mapping model. So we selected one single teacher, which is closer to the target language. So for example, in Javanese, it will be this Cebuano, which is 65%. In Cebuano case, it will be Javanese, which is 65, which is the maximum among them. So yeah. So you can see that with having single teacher, we got the improvement, average improvement of 43.2% to 41.4%, which is about 2% improvement.